long as, so I know I can get the process right.
Mhm.
I just need to know if I can get the actual answer. When did you state your exam was the 9th?
Yes, so it's not next week, the week after.
So we got this one on the 9th and 11th.
Same.
All right, well,
I have 4 in the next 2 weeks. Yeah. Depends on where the plastics one is. Well, I would say
no idea of plastics.
maybe there's somewhere. Should I start tomorrow?
Yeah. Yeah, I don't know. We'll get the answer to that.
Have you finished your abstract for the expo?
No, we're working on it today for we had a meeting for our senior design group at not 4, usually at 1, and we were working on it then. That's what I was working on for the manufacturing. I was just at E21. I just didn't want to. I wanted to work late into the night, and I know John's not available.
Right.
So, because I work better at night anyway. So I was just like, okay, well, let me just go to E21, start cutting.
Gotta shake that habit minutes when they age you.
Yeah.
We need to ask you, do you know if there's any info yet on what sessions, 476 lab will be?
Session B.
Session B?
Yeah. Mhm. Yeah, I don't know if it's up yet, but Dr. James told me it's session B.
Session B.
Yeah. Sure.
For those Dershowitz and Newman values
Mhm.
in rural application, will they automatically just be like zeros or?
It depends. And so, so zero is often used. And so, our Dirichlet boundary conditions for CFD are basically velocity conditions. So whenever you have like a solid surface, like a fluid's touching a solid, then you apply what's called a no-slip boundary condition there. And so you have a velocity of zero. So that's Dirichlet value of zero. For Neumann boundary conditions, those are most commonly pressure type boundary conditions for CFD. And oftentimes you have a stress-free boundary condition too. So basically a boundary where fluid can just pass right through without any impedance. That would be like a zero Neumann boundary condition. But you do have situations like, I'm working on the first open form activity. We'll probably do that the week after the midterm, where you have a non-zero velocity. So you have a surface that's basically moving, and that's applying a velocity. So that would be a Dirichlet boundary condition with a non-zero value. Yeah, so it really depends. It really depends on the situation. But zero is most commonly used just because of what it is.
Okay, I was kind of wondering, like, how does that, are we given that or just like?
Yeah, so
Starts with that zero.
right, so we'll talk about this when we get to more open foam stuff, but like the way you assign boundary conditions is based on whatever physical situation you're trying to simulate, right? Because most time when you run a simulation, it's a realistic situation that you're trying to just model in a computer, right?
Yeah.
And so you have to choose your boundary conditions that are most consistent with that physical situation. And so how you do that, of course, is I would say a little bit more of an art than a science. Because you do have to make some assumptions sometimes, because sometimes there's not a perfect boundary condition that perfectly captures what you're trying to do. But it comes with practice. And so yeah, we'll talk more about that once we get there.
Thank you.
Midterm pushed back because I guess one is on the second the next.
It's on March 9th. I don't think I planned it for March 2nd, but it's supposed to be for March 9th. Yeah. Yeah, we'll talk more about it next week. Yeah, I haven't even thought about it yet. I'll probably start thinking about it next week.
The lecture notes that you have on campus, are we still on 07 or?
We are on diffusion with finite volume, but don't know what number that is. Okay, yeah, so we're finishing that one today, and then we're moving on to the next one, which is 7, today's one. The convection with finite volumes. Okay. I have them printed in front of me, so I don't know what. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. All right, so plan for today. We have one more example to do for 2D diffusion. So we basically went over all the theory last time, and so we're going to see it applied into an example today. And then we're going to move on to convection. Okay. So I'm hoping we get all the content done with convection with finite volumes by next Wednesday. And that'll be kind of the cutoff for the exam, right? So if you weren't here, I know just people are joining on Zoom, just now, but the exam for this class is planned for Monday, March 9th. So that's not next Monday, that's the Monday after that. So we'll talk more about the midterm next week. I'll post a study guide next week as well. But just very basic information. So the exam will be in class. And so, for those of you on Zoom, please plan to come to the lecture. So it's a 75-minute exam. It's formatted very similarly to the homeworks in terms of there will be a short answer conceptual portion of the exam. There are going to be 3 problems that are planned for the exam. Yeah, I think that's about it. So with 3 problems, you can already make the distinction in your head. So we've had 3, we're gonna have 3 homeworks that are due up until the exam. So you can imagine there's gonna be one problem that's representing homework 1, another problem that's representing homework 2, and another problem that's representing homework 3. Okay, so that's always what I recommend people to study for my exams is to definitely do the homeworks. Go over them and so I'll post the solutions for the homeworks next week too. So when you're studying the homework problems, I always tell people don't just look at the solutions because you kind of trick yourself into saying like, oh yeah, I knew that, I understood that. But actually go through your homeworks and then actually try to redo the problems from scratch and then only look at the solutions if you need them. Okay. Because that's what it's going to be like on the exam. So on the exam, you're not going to have the solutions in front of you. You're going to have to kind of solve a problem from scratch yourself. Okay. You can bring a pencil, calculator, cheat sheet as well. So you can also bring 1 8.5 by 11 sheet of notes. You can use both sides. And so, yeah, so, all of that we prepare for next week. Okay, so we'll talk more in detail about it next week. I haven't really, thought too much about the exam yet. I haven't written it yet. So, but by next week, I'll have more information on that. Okay, but that's just the basics of what to expect for the exam. Okay. All right. Any questions I can answer before we get started for today? Yes.
With the material covered by the end of today, should we be fine to complete all of it?
So not yet. So homework for you do need some convection stuff, and so we're going to cover that stuff next week. So probably you won't be able to get everything for the homework until after Monday. Yeah. Mhm. All right. Any other questions before we begin? Okay. All right. So let's go ahead and get started. Okay. So last thing we went over before we left last week was 2D diffusion problems using finite volumes. Okay. All right, so let's just kind of recap very quickly. So diffusion equations, look like the following. Remember, diffusion is essentially our second order derivative, okay? So if we have, a situation that looks like this. All right, so that's our 2D diffusion equations. We have second order derivatives in x and y. We add them together, and then we have a source term on the other side of the equation, okay? All right, and so in finite volumes, remember the whole process of doing this in 2D finite volumes is we have our cell here, okay? And essentially, through the application of our finite volume technique, through the application of some of the integral rules that we did, okay? Essentially, what we saw is that when we discretize this equation, we essentially have to evaluate 4 different integrals, right? Because we basically took our finite volume integral, we split it into 4 using the divergence theorem, where each integral corresponds to a different edge or different side of our cell here, okay? Right, so we had a line integral on the north edge, a line integral on the east edge, a line integral on the south edge, and a line integral on the west edge, okay? Okay, so I'm not going to go through the whole details of that derivation again. We'll actually see it again very soon with convection. But essentially, you end up with 4 different terms, okay? And so after doing so, you get k multiplied by partial phi partial x, evaluated on the east face, delta y, plus partial phi partial y, evaluate on the north side, partial x, okay, minus partial phi partial x, evaluate on the west face, delta y, minus partial phi partial y, evaluate on the south side, delta x, okay? Where each of those derivative terms there, those are the derivatives of our solution evaluated at the centroid of our faces, okay? Right, and so in red there, I've pointed out kind of where you're evaluating those different derivative terms, okay? Now, what we plug in for those depends on whether we have a neighbor or not, or whether we have a boundary condition or not, okay? Okay. And so we essentially do different things depending on, depending. Okay. So this is kind of the name of the game with 2D finite volumes that, we basically break up our integral into different line integrals on each surface. And so, we're looking at square elements here, but you're going to apply the same methodology for triangle elements as well. Okay. And then you evaluate those integrals based on the information that you're given about that cell. Okay. Okay. And so that's going to be more or less the same when we do 2D convection. So I don't think we'll get to 2D convection today, but we'll probably do it on Monday. Okay, so let's put this into action. So let's do an example. Right, so a problem like this would be, very similar to what I would ask you. I mean, it's very similar to what I asked you on the homework. It's very similar to what I would ask you on the exam, okay? All right, so let's say that we have a particular domain. Okay. So this square right here is for the entire domain. It's not just a single cell anymore. Okay. And let's say we have the following boundary conditions. So let's say we have Dirichlet boundary conditions on the left and bottom sides. And let's say we have Neumann boundary conditions on the top and right sides. So we have partial phi, partial n is equal to 10 up top, and then partial phi, partial n is equal to 0 on the right-hand side. Okay. Okay, so let's say we discretize this into 16 cells. Okay, so let's break this up. So this will be cell 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. All right, so that's our two-dimensional domain along with our boundary conditions. Okay. And we also need a governing equation. So let's say our governing equation looks like the following. So you have partial phi, partial x squared plus partial squared phi, partial y squared. Okay. And let's say we have a source term here. So our source term is going to be 3xy. Okay. Diffusion constant is 1 in this case. All right. Let's do this too. So let's say that we have grid spacing is going to be 0.5 in each direction. Okay. Okay. All right. So given this information, we have everything we need to write out the finite volume equations for every cell in this grid. Okay. Now we're not going to do every single cell. That would be insanity. We take the entire lecture to do that. So let's just do a few of these. So let's write out the finite volume equations. So let's do cell 10, let's do cell 12, and then let's do cell 13. Okay. Okay, so we're going to do these 3 cells here. So 10, 12, and 13. Okay, so that gives us a pretty good mix of, we have one interior cell, we have one cell that has a boundary condition on one edge, and we have one corner cell, right? So I think the last thing we talked about last time was how to deal with corner cells. So you're actually going to see that here. Okay. Okay. All right, so let's go ahead and get started. Let's start with cell 10. So cell 10 is the easiest one to do. Okay. So what do we notice about cell 10? So cell 10 has a neighbor on every side, right? So north, south, east, and west, we have a neighboring cell there. Okay, so cell 10 is what we characterize as an interior cell. Okay. Now, interior cells are great because, we have a formula for that, and they basically all kind of follow the same. Okay. Right. Okay, so this is the formula we derived kind of in the middle of class last time, right? So this is one, like I said, with the boundary conditions, we can't really come up with the general formula. You kind of have to do those ones kind of one at a time just because of how they are. But for all the interior cells, they all have the exact same pattern. Okay. Okay, so for interior cells, we have the following equations. We have basically K, or actually, let me do this. So for interior cells, we have the following stencil. So we have phi big E plus phi big N plus phi big W plus phi sub S minus 4 phi sub C is equal to Q at XC comma YC multiplied by delta squared. Okay. right? So every interior cell follows the same pattern. So the only thing that's interesting or different is that, you know, whatever is on the right-hand side with the force term, okay? Oh, one thing I did forget, we do have a K here, okay? Although in our case, K is 1, so it doesn't really matter, okay? All right, so let's go ahead and plug in. All right, so let's note what the east, north, west, and south neighbors are for cell 10. Okay, so the east neighbor for cell 10 is cell 11. Okay. So phi underscore E is going to be phi 11 plus the north neighbor. So north neighbor for cell 10 is cell 14. Okay. Plus the west neighbor. So the west neighbor for cell 10 is going to be cell 9. Okay. And then the south neighbor is the one right below it. And so that is cell number 6. Right, so we get kind of a nice balanced stencil for all neighbors, and they're all kind of contributing equally, minus 4 times the central cell, where of course the central cell is cell 10. So minus 4 times phi 10. Okay. All right, next we have our source term. So our source term in this case is 3xy. Okay. So we're going to have 3, right? So I'll only do this for the first cell, but you know, just know that it's the same for everyone, right? Remember when we're computing the coordinates, right? So this is going to be xc, yc. We're looking for the physical coordinates of the center of the cell, right? So we're essentially looking at, you know, what is the x coordinate here? Okay. And then what is the y coordinate here? Okay. So we know, right? We know from the problem that the grid spacing in each direction is 0.5, right? That means the length of the cell in each direction is 0.5 meters, I guess you can say. Okay. Right. And the centroids of each cell are in the center, right? And so, you know, if we look at xc for this problem, or for this, you know, for this cell here, for cell 10, we can see in order to get over to cell 10, we cross over cell 1, we get halfway between cell 2. So that means xc here is going to be 0.75. Okay. And then yc in this case is going to be 0.5, 1, 1.25. Okay. And then we multiply this by the grid spacing squared. Okay. So this is going to be 0.5 quantity squared. Okay, and so of course, you know, normally you would simplify that, but you know, I do want to get to convection today, so I'll just kind of box it just like that. Okay. All right, so that's our first equation. So you know, interior cells, very straightforward. We just apply the stencil as it is. Okay. Any questions on how we got that equation there? Yes.
Can you repeat how you got that 0.75 and 1.25?
Sure. Yeah, so xc and yc, these are basically the physical coordinates of the center of cell 10, right? Yeah, so we're basically looking, if we imagine this is kind of like a coordinate axis, right? So this is the x-axis, y-axis, and we just know the grid spacing, we just, you know, find the coordinates of that.
Thank you.
Right, any other questions on this part here? Okay. All right, so let's move on to the next cell. So the next cell in this problem is cell number 12. So cell number 12 is not an interior cell. So we do have a boundary condition on this one, right? So on this case, we have a Neumann boundary condition of 0 on the east side of the cell. I think it was only one, whatever. Okay. Yes, question.
The previous one,
Mhm.
you did divide by k.
So in this case, K is 1. So there's no K in this case. So yeah, so it's kind of implicitly, but yeah, normally if you do have a K, you do have to divide. Question, yes.
That K is what's outside of the partial part.
Exactly, yeah. So if we did have a K, so let's say that for this problem here, we had a, I don't know, like a 5 here. So in that case, 5 would be the K. But in this case, it's 1, so we just, you know, we just kind of ignore it. Yeah.
There's no case where we got two different for each one of the partial? Or-
You could. So technically you could you could have different diffusion constants in each direction, but those are kind of more, how should I say, mathematical what's more mathematical trivia. Yeah. So for physical situations for diffusion doesn't really pick a direction, and so you have basically the same diffusion constant in each direction. But technically, yes, technically you can have different constants for each of the derivatives. Mhm. Okay. All right, so for cell 12, so we have a Neumann boundary condition on the east. Okay. So since we don't have a neighbor on the east side, we can't just use our generic interior cell stencil. And so we do have to go out based off kind of the general formula here. Okay. Right, keeping in mind that for this cell, we're going to be replacing this derivative here, with the boundary condition. Okay, so for this expression here, I'm going to ignore the k just because we know the k is 1 for our case. Okay, so for cell 12, we're going to have partial phi partial x on the east side, delta y plus partial phi partial y on the north side, delta x minus partial phi partial x on the west side, delta y minus partial phi partial y on the south side, delta x. Okay. And this is all equal to q xc yc. Oh, I forgot the delta squared. Delta squared. Okay. All right. So for all the other derivatives here, so let's do those first. I think this will be a good reminder in terms of how we evaluate these, right? So for all the other derivatives, remember the way that we evaluate them is we essentially use a central difference scheme based on the center cell and the neighboring cell. Okay. And so for partial phi partial y on the north side, this is equal to phi on the north minus phi sub c, all divided by delta y. Okay. For partial phi partial x on the west face, this is phi c minus phi w, all divided by delta x. Okay. And then for the last one here, we have phi c minus phi sub s, all divided by delta y. Right, so if you have a neighbor, essentially those derivatives we evaluate just using this very simple central difference. Okay, now for the boundary condition. Okay, so for this boundary, right? So for cell number 12, the right-hand side, let's go back up to the figure so we can see. Okay. So for this Neumann boundary condition, we can see that we have a derivative value equal to 0. So I think the solution value going to the right on that boundary is going to be equal to 0. Okay. So you have partial phi partial n is equal to 0. Okay. So this is our boundary condition. Okay. So remember, Neumann boundary conditions are very easy to apply in finite volumes. We just basically just replace that derivative. Okay. And so if the boundary condition says this is 0, well, that means that whole thing is going to cancel out. Okay. So then all we're left with here are just these basically these finite volume terms here, or these these central difference terms. Okay. And remember, we are making the assumption that our grid spacing is the same in delta x and delta y. Right, and so we plug in this central difference. That means this delta y is going to cancel with this delta x. Okay, this delta x is going to cancel with this delta y. Okay. Now, if your grid spacing weren't the same, then you'd have some scaling factor there, and you would have to account for that. But for everything that I would give you guys, we're just going to assume that the grid spacings are the same, just for simplicity. Okay, I wouldn't throw you that curveball just because it just ends up just being busy work more than. Okay, so let's go ahead and evaluate everything here. So we can go ahead and simplify. Okay. Okay, so when we simplify everything, we get phi sub n plus phi sub w plus phi sub s minus 3 phi sub c. Okay, this is equal to 3 xc yc delta squared. And then just like we did with the previous part, we just plug in the appropriate number of the node numbers, or excuse me, the cell numbers for the neighbors. Okay. So the north neighbor for cell 12 is cell 16. Okay, so this is phi 16. West neighbor for cell 12 is going to be phi 11. South neighbor for cell 12 is going to be phi 8. Right, and so that is our equation there, where XC and YC, we can go ahead and plug in those values too. So XC, YC, that is the physical coordinate of that cell, right? So for cell 12 is all the way on the right-hand side. So that means XC here, that's going to be 1.75, okay? And then YC, it should be the same as cell 10, is 1.25. All right, any questions on that part of the example there?
Why did the bottom row get constant?
Bottom row. Oh,
Yeah.
so when we plug in these finite differences, right, we divide by the grid spacing, but we still have these grid spacings here from the original kind of expression. Oops. Right. So I think this is an important point to bring up, right? So remember these grid spacings here, right? Let me highlight them in blue. Okay. So those grid spacings there don't come from finite differences, they come from our application of trapezoidal rule, right? Because we're essentially evaluating an integral on that edge, right? And that's different from these grid spacings. And so these grid spacings come directly from the finite difference, from the central difference. And so in our case, since we assume them to be the same, we have one in the numerator, one in the denominator, they just cancel each other. Yeah.
Because it's the same.
Exactly. Yeah. 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 For everything I'll give you, you can always assume that delta X, delta Y are the same. Good. Okay, any other questions on this part here? Yes.
Can you explain one more time where you can cross that down?
Oh yeah. So this one, right? So for cell 12, actually, let me draw the schematic down here, right? So we have cell 12 here. Right? Above it, we have 16. To the left, we have cell 11, and to the bottom, we have cell 8, right? But on the east side, we don't have a neighbor, but we have a boundary condition. Right. So just for this particular problem, that Neumann boundary condition there just ended up being 0. Yeah, and so boundary conditions, that's another thing that I will always give you. That's not something you kind of make up or determine on your own. And so it's just kind of applying that boundary condition to that. So in this case, it ended up being 0, and so it ended up just kind of canceling out. But you'll see on the next one that we do, we're going to do boundary conditions that are non-zero, and so you'll see how that factors in. All right, any other questions on this part here? Okay, all right, so let's do the most interesting cell. So let's do cell, what did I say, 13. Okay, so cell 13 is very interesting. So that's one we haven't done an example of yet. So that's one we kind of just talked about in general at the end of class on Monday. So cell 13 is a corner cell. Okay. And so what that means is that it's going to have a boundary condition on 2 of its edges. Okay. So in this case, we have a boundary condition on our west edge. Okay. And that is a Dirichlet boundary condition, I believe. Yep. So Dirichlet BC on west edge. Okay. And then on our north, we have a Neumann boundary condition. All right, so we have 2 boundary conditions that we need to apply at the same time. Okay. Now it seems challenging, but with our approach where we kind of go straight from the derivatives, you'll see that it's more or less kind of straightforward. Okay. So actually, let me do the same thing I did for cell 12 right there. Let me go ahead and draw the schematic. Okay, so this is cell 13 from our grid. To the right, we have our neighbor, cell 14. And then we do have a neighbor to the south. And so this is cell number 9. Okay. On the left-hand side, we have a boundary condition. B is equal to 50. And on the north side, we have partial phi partial n is equal to 10. Okay. All right, so we're going to follow the exact same process we did for cell 12, except now we're going to apply boundary conditions on 2 of our derivatives instead of just 1. Okay, so just like we did with cell 12, let's go ahead and start with the general formulation here. Okay. So you have partial phi partial x on the east face, delta y, plus partial phi partial y on the north face, delta x, minus partial phi partial x on the west face, delta y, minus partial phi partial y on the south face, delta x. Okay. Guess we particularly don't need parentheses there. All right, and this is equal to 3xc yc delta squared. Okay, so first thing we'll do, let's go ahead and replace and put the derivatives in there for the sides where we do have neighbors, right? So we have neighbors on the east and the south side. Okay. All right, so for the east, and just to kind of save some time here, we can just go ahead and plug in the exact neighbor. So we know that our neighbor on the east is cell 14. So this is going to be phi 14 minus phi 13 divided by delta x. Okay. And then the other one that we know is south side. Okay, so for the south side, we have phi 13 minus phi 9, all divided by delta. Okay, and then just like before, the delta x's and delta y's will cancel out, so we don't have to worry about this. So that cancels there. That cancels with that. Perfect. Okay. All right, so now we have our 2 boundary conditions one. So let's start with the north, because that's pretty much the same as what we had previously. Okay, so on the north edge of this cell, right, we have a Neumann boundary conditions that said that partial phi partial n is equal to 10. All right, so we're basically just going to replace that entire derivative expression with just the boundary condition value, which is 10, right? So remember, Neumann boundary conditions, they are a condition on the derivative of the solution, okay? And that's exactly what we have there in our expression there. So this is going to be 10 times delta x. Okay. Plus. Okay. All right, so for the Dirichlet boundary condition, I'm going to go the other way, just because it's getting kind of messy on the bottom. Okay. So for the Dirichlet boundary condition, remember how we did this, right? So, let me go ahead and draw this into the figure here. Okay. So remember, the value of the solution at the center of the cell, this is where phi 13 is, right? So phi 13 is a value there. Whereas at the west edge, right, we know exactly what the value of phi there is going to be, which is 50. So if you remember from last time, I think even the time before that, remember the way that we evaluate that space derivative is we essentially just do a central difference, but with a half grid spacing. Okay. So the grid spacing between basically this point and this point is delta x divided by 2. Okay. All right, and so this derivative here is going to be phi 13 minus 50, all divided by delta x divided by 2. All right, and where again, we have a delta x in the denominator, we have a delta y in the numerator for this term, and so those are going to cancel. Okay. All right, so a lot going on there, but hopefully everything is clear. We'll simplify that in a second. But any questions on kind of how we replaced each of those terms there? Yes.
Just for like a programming perspective, is it okay to call that like your theta or your phi naught?
Yeah, you can do that too. Yeah, so I just plugged in 50 just because that just happened to be the value there. But if you want to keep this generic, you can definitely plug in phi not here. That's like a given value for the Dirichlet. Okay, all right, so let's go ahead and simplify and then let's wrap up this example here. Okay. All right, so let's go ahead and write every expression down here. So we have phi 14 minus phi 13 plus 10 delta x. We have a 1/2 in the denominator for this blue term here, so I'm just going to put it up into the numerator. So this is going to be a minus 2 phi 13 plus 2 times 50, which is 100. Okay. Minus phi 13 plus phi 9 comes from the south derivative. Okay. And this is equal to 3xc yc delta squared. Okay. All right, so now all that's left is just to simplify. So everything that's not a phi term, right? So everything that's known, we can go ahead and move it to the right, right? So that means this 10 delta x and this 100 here, we can go ahead and move those to the right-hand side. Okay. And then all that we're left with here is basically phi 14 plus phi 9 minus 4 phi 13. That should be right. Is equal to 3xc yc delta squared minus 10 delta x minus 100. Where, just because we're here, let's go ahead and write out the coordinates for xc, yc, right? So xc for cell 13, that is on the very left edge. So xc here is going to be 0.25. And then yc, this is we're at the very top of the domain. So this is 1.75. All right. So one thing you should know, right? So one thing, you should definitely do this whole process for every cell that has a boundary condition, right? Because the signs of things will change and everything like that. But one thing you should notice is that for every boundary condition that we have, our stencil on the left-hand side kind of gets reduced by one neighbor, right? So if you look at this, right, we only have two neighboring cells here, which is set phi 14 and phi 9, right? Which is 2 less than our interior cells. For the interior cell, we have 4 neighbor contributions. It seems like an obvious thing, right? So, if you don't have neighbors, it shouldn't show up in the equation, but that's always good, good, I would say, sanity check for you to do, when you do get these expressions, because yeah, there's a lot of kind of moving pieces. There's a lot of algebra to do. There's a lot of indices kind of flying around. And so, it's always good to have kind of a way to kind of check your solution to make sure that it all kind of makes sense. All right, any final questions on this before we move on to convection? Yes.
Can you scroll up to show what you did on
Yes. Yeah, so for that 100 term, that was our Dirichlet boundary condition. So our Dirichlet boundary condition for this problem was 50. But because we had that 1/2 in the denominator, that 2 kind of comes up and multiplies by the 50. So then that 50 times 2 becomes 400. Yeah. Any other questions on this problem here? Okay. All right, so let's go ahead and move on to convection. Okay. All right, so this is kind of the last thing that we'll do with finite volumes. And, there's going to be a lot of repeat information here because we've already done convection with finite differences. Okay. So I don't really need to explain what convection is, but just to kind of just for completeness, right? Convection, remember, is the force transport of a material through a moving fluid. Okay. So the general convection diffusion equation in 2D is the following. Okay. We have basically the divergence of some velocity vector multiplied by our solution phi minus k. Divergence of the gradient of phi is equal to q of x and y. Okay, so this is our convection diffusion equation in multiple dimensions in vector form, okay? Where the kind of the most important part of this is this v. This is our velocity field, or velocity vector, I guess you could say. Okay? Because remember, with convection, we have a situation like this, where we have some kind of moving fluid, okay? Where the velocity streamlines here, that's essentially our fluid velocity. That's our convection velocity. Okay. All right. So that convection velocity does bring some complications, right? And so, remember with convection, we were first introduced to this idea of solution stability. And so the same thing can happen with finite volumes. And so for finite volumes, we can get unstable solutions. And so you'll see that, a lot of the techniques that we learned in finite differences, they'll have kind of the same concept in finite volumes, just applied somewhat differently. Okay. So we're going to see things like our Peclet number. We're going to see things like upwinding. Okay. Right. So all of these same concepts still apply. It's just that the way we actually, implement them, the way we actually compute them is slightly different because, finite volumes is different than finite differences. Okay. Okay. But that's just kind of a preview of where to go. Let's start very simple. Let's start with the 1D convection diffusion equation. Okay, so our 1D convection diffusion equation looks like the following, right? So we have d dx of our fluid velocity u multiplied by phi minus k d dx of d phi dx, okay, is equal to q of x, okay? And of course, this is a situation where, we have a one-dimensional domain, just like this, okay? Right, and we have a fluid velocity. Just for the sake of argument, let's say it's going from left to right. Okay. And we want to solve for the evolution or the distribution of phi as a function of x. Okay. Okay. All right, so just like we did with diffusion, our first step here is going to integrate this equation. Okay. So in order to perform our integration, we do need our finite volume cells. So let's consider a single cell here, right? So let's kind of trap or bracket that cell there. Okay. With the left-hand side of the cell, it will be x sub L. The right side will be x sub R. Okay. Right. You can pick any cell. So I've chosen that cell arbitrarily. And so the idea is to do our integration and get our equations in a way that's generic that we can apply to almost any problem. Okay, so just like we did with diffusion, we're going to take our governing equation and integrate it along the length of the cell. Okay, so let's go ahead and do that. Right, so I'm going to invoke the fact that integration is a linear operator, so I'm going to integrate each term individually. Okay. So we have integral from XL to XR of d dx, u times phi dx, okay, minus integral from XL to XR of k d dx of d phi dx dx is equal to integral from XL to XR q of x dx. Okay. So I just took our 1D convection diffusion equation and I just integrated every single term from the left side of the cell to the right side. All right. So at this point here, we're going to evaluate every single integral here. So on the left-hand side, we're going to use our one-dimensional divergence theorem, or as we like to call it from before, just evaluating the integral, right? So we don't have to do anything special there. Just so the dx's are going to essentially cancel out. And then on the right-hand side, we're going to use our trapezoidal rule just to evaluate that at the centroid of the cell. Okay. Okay. So we go ahead and evaluate these. We see that our dx here essentially just cancel out. Okay. And so we have integral of these kind of perfect differentials here. Okay. And so we evaluate those integrals. What we get is product of u times phi evaluated on the right-hand side of the cell, okay, minus u times phi evaluated at the left-hand side of the cell, okay, minus k times d phi dx evaluated at the right-hand side of the cell, minus d phi dx evaluated at the left-hand side of the cell. Okay. And then right-hand side, we have q at xc multiplied by delta x, where delta x is just the difference between xr and xl. Okay. All right, so we have something interesting here. So on the one hand, we have something familiar, right? So these diffusion derivatives we've seen before. Okay? So remember, these are essentially our solution derivatives. Okay? Evaluated at the edge of our cell. Okay? So essentially identical to the example we did earlier. It's just they're on 1D. Okay? So let me go ahead and draw our cell one more time. All right, so this is our cell. So let's say that our central value here is phi sub c. Okay. But we also have a neighbor to the right, and so that is phi sub big E, and our neighbor to the left is on the west side. So I say phi sub W. Okay. Okay. Where this bracket here, remember, this is x sub L. This bracket here is x sub R. Okay. Okay, so we know how to evaluate these derivative quantities because they're evaluated at the edges of our cell, right? So for instance, d phi dx at x sub R is evaluating that derivative at that location there. Okay. And so essentially the way that we're going to do that is we're going to evaluate it using finite differences. And so this is going to be BE minus phi sub c all divided by delta x. Okay. And then this one here, evaluated at this edge right here, this is going to be phi sub c minus phi sub w all divided by delta x. Okay. Okay, so that's the same as before. So there's nothing new for that. So diffusion is still a part of this equation, and so we have our diffusion contributions. Those have not changed. Okay. What has changed, of course, is the addition of these convection terms. Okay, so these convection terms are interesting because, we no longer have derivatives here, right? So we basically applied, that's part of the reason why we integrate is to get rid of that derivative, right? And so instead of evaluating the derivative of the solution at the cell faces, we're now evaluating just the solution itself at the cell faces, right? So this phi sub u times phi at phi sub L, that's the same phi that's evaluated here. And this phi sub u times phi evaluated at x sub r is the same solution evaluated at that face. Okay. Okay, so let me just write that in words here, just because that figure very quickly became a mess. Okay. So to evaluate the convection terms, need to compute so we need to compute the value of phi, which is our solution, at the edges of our cell. Okay. So the velocity I'm not worried about. The velocity is usually pretty easy to compute. If it's not constant, it's usually a very simple function of x. And so, that one I'm not too worried about. The one that's interesting here is the phi, right? And so you might be asking, why is that an issue? Why is that an issue that we, have to compute phi at the edges per cell? Well, that's not what we're trying to work with, right? So remember, we are working with what's called cell-centered finite volume, right? And so the issue here is that, we don't evaluate the value of phi at the cell edges. We evaluate them at the cell centers. Okay. All right, so we're going to need some way to kind of reconcile these 2 points where our equation is demanding that we evaluate phi at the cell edges, but the way we're discretizing, the way we want to store the solutions, the way we want to do our computations, we only want to evaluate phi at the cell centers. Okay. Okay. So let's see how we can rectify that. Okay. Okay. So first thing we'll do, let's do on the right-hand side. Okay. So essentially we have phi sub r. Okay. So phi sub r here is right in between phi sub c and phi sub big E. Okay. Okay. Right. And so the simplest thing we can do is basically assume that, the value of phi just varies linearly from our cell-centered value to our east neighbor. And so if we evaluate the value of phi right in between, it's just going to be the simple average between the two. So we can say that phi sub little r here is phi sub c plus phi sub e divided by 2. Okay. Right, and we can apply that exact same logic on the left-hand side. So phi sub L is right in between phi sub C and phi sub W. Okay. So the average between those two is phi sub C plus phi sub W divided by 2. Okay. All right, so let's go ahead and plug those two into our expression up there, and then I'm going to go ahead and plug in the finite, the finite difference expressions for the derivatives. Okay. Okay, so we do that. We end up with U multiplied by our convection terms here. So that's phi sub C plus phi sub E divided by 2, okay, minus phi sub C plus phi sub W divided by 2. Okay. So those are our convection contributions using the basically the averaging technique that we just went over just above here. Okay. Then we have our diffusion contributions. So our diffusion contributions is a K times phi sub E minus phi phi sub E, sorry, phi sub E minus phi sub C divided by delta X minus phi sub E minus phi sub W divided by delta X. Okay. And this is equal to Q XC YC delta squared. Okay. Right. Question, yes.
Why is there a Y C?
Oh, sorry, there's no Y. Thank you.
Oh,
I was jumping ahead to 2D already. Yeah, should just be Q of X. All right, and so now we've kind of fixed our problems. We don't have any cell edge values anymore. Everything is evaluated in terms of the cell centered values. So now all we just need to do is just simplify. Okay, so here's the interesting thing. And so for the convection term, we have a positive phi sub c divided by 2 and a minus phi sub c divided by 2. So these two are actually going to cancel out. And so all we end up with is u times phi sub e minus phi sub w divided by 2. Okay. And then for the diffusion term, we have a delta x that comes out from the denominator. So I'm just going to factor that out there. And then we have phi sub e plus phi sub w minus 2 phi sub c. Okay. All this is equal to q at xc multiplied by delta x squared. Okay. Okay. All right, so then last thing we need to do here is that usually the way we simplify this is that we kind of group the terms according to their corresponding phi values, right? Essentially, we just want a coefficient in front of each phi value just so we know what to plug in for each of these, right? Okay, so for phi sub e, right? So the coefficient for phi sub e, we have a u divided by 2 minus k over delta x multiplied by phi sub e, okay? Plus, now we have the coefficient in front of phi sub w, so this is a minus u divided by 2 minus k over delta x, phi sub w, okay? Plus 2k over delta x, phi sub c is equal to q at xc delta x squared, okay? And that is our equation there. Okay, so this is our finite volume equation. Okay. For convection diffusion. In 1D. And remember, this is for an interior cell, because remember, we have neighbors on the left and right. Okay. Any questions on this? Okay. All right. So, when we have convection here, the kind of the order of business is to see, the main thing we need to determine is how we're going to treat these face values here. Okay. Now, the next thing in the notes, and so if you're kind of following along the notes, is, we go over the boundary conditions. But I think we saw enough of that today, and so I think I'll save the boundary conditions for Monday. And so the last thing I want to go over today is talk a little bit more about these phase treatments here, because how we actually treat this ties directly into upwinding. Okay. Okay. So let's talk about upwinding in finite volumes. Okay. All right, so let's do a very quick refresher in terms of what upwinding was, remember? So let's recall. Okay. So remember, when we have convection, flows or situations with convection, we have to start worrying about solution stability. Okay. So convection can introduce instabilities okay. Right. So because of the nature of how the convection term is formulated mathematically, we can start to have unstable solutions. Okay. So how do we deal with this before, right? And so if you recall from finite differences, right, there's kind of two paths that we can take to get stable solutions. And so on one path, let's say that we're very stubborn and that we want to keep our central difference scheme for our convection derivative. Okay. So there's a lot of benefits to using central difference, remember. So remember, central differencing does have better accuracy, right? And so if you can make your solution stable with central difference, you're going to end up with a more accurate solution. Okay, so remember, for central difference, that basically means that, our dph dx is equal to phi plus 1 minus phi minus 1 divided by 2 delta x, right? So essentially, we had kind of a balanced finite difference scheme for our convection derivative, which is a first order derivative. Okay. All right, so the way that we checked this, or the way that we made sure that it was stable, we computed a special number called the Peckway number. Right? I still have to wear the Sanrio shirt. Don't worry, I don't forget. All right, so remember, the Peckway number is the product of the velocity multiplied by the grid spacing divided by the diffusion constant. Okay. All right, and then if our Peckway number is less than 2, right, either by some combination of our velocity or diffusion constant or our grid spacing, right? If that's true, then our central difference scheme will be stable. Okay. The other way that we can achieve a stable solution is to change our discretization scheme. And so instead of using a central difference, we applied what's called upwinding. So upwinding was kind of a twist on how we applied our finite difference, where we changed the type of differencing scheme to place more weight or more emphasis on the upstream side of the flow. Okay. Right, and we kind of rationalize this by saying that, when flow, when you have velocity, right, velocity always has a certain direction, right? It always goes from one side to another, top to bottom, left to right, and so on and so forth. Okay. So since information travels, we say that information travels along the direction of the velocity. It makes sense, for our differencing scheme to be more weighted towards where the information is coming from. Okay. Okay. So basically, for upwinding, right, we would change the way we discretize our derivative, right? So we would say dph dx, let's say we use a backward difference scheme, so phi minus phi I minus 1. Okay. Right, so a backward differencing scheme would place more emphasis on the left-hand side of our stencil. Okay. Right. So that's great for when the velocity is going from left to right, right? And so that's essentially when our velocity is positive. Okay. Right. So if u is greater than 0, what we saw before was that we changed our differencing scheme to backward difference. Okay. But what if our velocity is negative? So if our velocity is going from right to left, then we're going to change our differencing scheme to a forward difference. And so this can be phi I plus 1 minus phi I divided by delta x. Okay. So this, of course, puts more emphasis on the right. Okay. And that's good when u is less than 0. Okay. So that's just a quick refresher of that. So that all that was just finite differences, right? Now, how does this apply to finite volumes? Because there was never a point in our derivation here where we said, we're going to apply a central difference scheme. Well, technically we did, but it's for a diffusion, right? I would make the argument that we have already made that decision, okay? Right? So that decision in terms of how we want to discretize the convection has to do with how we estimate or how we approximate the cell face values. Right, so for finite volumes, choice lies right? So how we choose to approximate that, that's going to tell us whether we're using a central scheme or central-like scheme or an upwinding-like scheme. Okay. So for example, right? So what we've used so far is that when we try to estimate phi sub little r, right? Where phi sub little r, that's the value of phi at the right-hand edge of our cell. What we said was that was simply just the arithmetic average of our two neighboring cell-centered values, right? So this is phi sub c plus phi sub big E divided by 2, and phi sub little l is equal to phi sub c plus phi sub w divided by 2, okay? So this right here, this decision to say that we want to get the cell face values, we're just going to split the difference between the two. This is a central like scheme. Right, and so because of that, if you go with this scheme right here, you could end up with unstable solutions if the Peclet number is greater than 2. Okay. So then how else can we do this, right? So, this seems to make the most logical sense, right? Because physically, that cell face is located right in between our two cell-centered values. And so, what else can we pick for this, right? So let's look and see what the upwinding scheme looks like. Okay. So actually, let me do this. So let me go ahead and draw our domain here again. So let's say we have our cell-centered value here. So this is phi sub c. Okay. right? And we have the neighboring cell-centered values as well. So phi sub E and phi sub W, okay? And remember, what we want to estimate is the value of phi right in between those two cell-centered values. So this right here would be phi sub little r, and right here, this would be phi sub little l, okay? Okay, so let's see if we can come up with different expressions for those. So phi sub little r and phi sub l for the case when we want to apply upwinding. Okay, now, of course, when you have upwinding, it's of course going to depend on the direction of the velocity. So let's say, just for the sake of argument, let's say that our velocity is greater than 0. So it's going to go from left to right. Okay. All right, so if our velocity is going from left to right, that means we want to put more emphasis in our discretization on the left-hand side of our domain. Okay. Right, so we want to emphasize the left. Okay. Okay. So let's start with let's actually start with phi sub little l, right? So that is the self-centered value on the left edge of our cell. Okay. Okay. So phi sub little l, it's right in between phi sub w and phi sub c, right? Previously, we said that physically it's right in the middle. So let's just take the average. Okay. The other extreme that we can do is that we can just say that the value of phi sub l is going to be equal to the cell-centered value right to its left. Okay. So what if we said that phi sub l is simply just phi sub w? Okay. Right. So that's basically the closest cell-centered value right on the left of phi sub l. Okay. Same thing for phi sub r. So phi sub r, right? Right. We can use phi sub c for this, right? Because that's the closest cell-centered value that's to the left of phi sub r. Okay. Now, of course, this is a little bit extreme, right? And so we went from taking the average between the two, and now we just say forget the other one. We're just gonna choose one side here, right? And obviously, you can tell. So from here, I think it's even more obvious that when you upwinding, this is going to be a lot less accurate than the central scheme, right? Because instead of taking the average between these two things, we're basically just approximating it using only one value, right? So this obviously is going to be less accurate. Okay. But at the very least, it is going to be stable, right? And so we are going to get a stable solution because we're putting more emphasis on the upstream side. Right? Now, of course, if you do this is going to change our finite volume equations. And so I think last thing I'll do today is, we'll kind of illustrate what that looks like. Okay. And you'll see it kind of has the exact same effect as in finite differences, where we're changing kind of the emphasis of the different terms, the weighting of the different terms in our finite volume equation. Okay. All right. So let's go ahead and plug those in. Okay. Okay. So let's go back to our finite volume equations, and let's start from the part where we plug in the face values, right? So this is the finite volume equation for 1D convection diffusion. Okay. Okay. So we have U times phi evaluated at little r minus U at phi evaluated at little l, okay, minus K d phi dx evaluated at x sub r plus K d phi dx evaluated at x sub little l, okay? And this, of course, is equal to Q of xc multiplied by delta x. Okay. Okay. All right, so let's go ahead and plug in our upwinding values for phi sub little r and phi sub little l. Okay. Remember, our diffusion terms don't change, so diffusion is always going to be the same. So essential difference is always the best for diffusion. Okay. And so we do that, we get u. Okay. Phi sub little r is now going to be phi sub c, okay, for the case of a positive velocity, minus u. For phi sub l, we're just going to plug in phi sub w, okay, minus k. Our derivative here, we're still going to use a finite difference. And so that's going to be phi sub e minus phi sub c all over delta x plus k, phi sub c minus phi sub w multiplied by delta x. Okay. Right-hand side is unchanged. And so right-hand side is still going to be q of xc multiplied by delta x. Okay. Okay. All right, so just for the sake of time, I'm just going to simplify this in one step, but you know, if we have everything here, it's just simplifying and grouping the like terms. Okay. And so we simplify everything, we get a minus u plus k over delta x, or excuse me, minus k over delta x, phi sub w, okay, plus minus k over delta x, phi sub e, that's the east neighbor, right? So you can see that we no longer have a velocity coefficient in front of phi sub e, right? So that's been shifted over to phi sub c, okay? And then for phi sub c, we have a u plus k, or 2k over delta x, phi sub c, and all this is equal to q xc times delta x. Okay. Okay. So right here is our upwinding finite volume equation for u greater than 0. Okay. Now, of course, if your velocity was negative, you would then upwind in the other direction. So you'd place more emphasis on the right, right? And then that, of course, would change your equations here as well. But that's essentially how you perform the upwind. Okay. Now, you might be asking, right? The way we did upwinding here was a little bit extreme, right? So we just said that, you know, we're just going to take just one of the values there. So what if we do a weighted sum instead, right? So what if we do like 1/3 phi sub c plus 2/3 phi sub e, right? And so that concept it is a real thing, but we're not quite ready to discuss that yet. So we'll discuss that when we go over higher order convection speeds after Computational. Okay. All right. Any final questions before we wrap it up for today? Yes.
Your question about prior equation.
Yeah.
How did we somehow get all the way up
Oh,
actually for the 1D convection fusion?
Yep.
How in the end did we get x squared?
Oh, that is a mistake. It should just be x. Yes. My mind was on the 2D stuff already. So yeah, it should just be delta x. Yeah. Thank you for that. Yeah, it should just be delta x. Yeah. Okay. All right. So I'll stick around for a bit if you guys have any questions. I know it's over time. So thank you guys for coming today. I hope you guys have a good weekend, and I will see you all next week. Thanks, guys.
Off the machine, so how to get that. Other than also not. If you try to like, you hit the, he has to reset it.
No.
Yesterday.
No. No, it's so I marked you as an auditing.
This is pretty straightforward.
You don't have to.
There's a chance.
It is our meeting.
Well, I know that, I mean, I'm working on my.
I'm not sure. What's the measurements on that? 875.